Okay, let us consider again another example of a ring with zero divisor. If you take set 6 which contain the elements 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, then we know that set 6 under the addition modulo 6, multiplication modulo 6 is a ring, where the addition modulo 6 and multiplication modulo 6 are defined in this way. A bar plus B bar under addition modulo 6, this gives you the remainder obtained when the sum A plus B is divided by 6. And the product A bar into multiplication modulo 6 B bar, this also gives you, will be, the value of this one will be the remainder obtained when the product A into B is divided by 6. Now, these are the table for that one. And addition modulo 6. So 0 bar plus 0 bar and addition modulo 6 will be 0 bar. So with 5 bar, you add 0 bar to 5 bar, then it will be 5 bar. Now 1 bar you add to 0 bar, it will become 1 bar. 1 bar plus 1 bar, it is 2 bar because it is still less than 6. So that will be the remainder. So 1 plus 3 will be 4. Since it is still less than 6, so the value of that one will be 4 bar only. 1 plus 4 will be 5. Since it's still less than 6, so it will be 5 bar. Now when you add 1 with 5, then it will become 6. So on dividing 6 by 6, the remainder obtained will be 0 bar. So you will have the entries here as 0 bar. Similarly, if you take 4 bar with 3 bar, 4 bar with 3 bar will become 7 bar. 7 bar on dividing by 6, 7 on dividing by 6 gives you the remainder 1 bar. So you have to write entry here as 1 bar. So 4 plus 2 will be 6. 6 divided by 6 gives you the remainder 0 bar, and so on. Let me just take this last one. 5 bar plus with 2 bar, it becomes 7 bar. So 7 on dividing by 6 gives you the remainder 1 bar. So you have to write the entry 1 bar here, which is the remainder. Then 5 plus 3 will be 8. 8 on dividing by 6 gives you remainder 2. So you have to write 2 bar here. 5 plus 4 will be 9. 9 on dividing by 6 will give you the remainder 3. And 5 plus 5 will be 10. On dividing 10 by 6 gives you the remainder 4 bar. So you can see from this table, it satisfies this one. The closure property, associativity will be satisfied. Why? Because we know that the set of integers satisfy the associative law, and this also will satisfy that one because we define the sum of these two, A bar and the addition modulo 6, B bar modulo 6 will be equal to the remainder obtained when the sum A plus B is divided by 6. We know that this one is where A and B are integers only. So satisfy the associative law. Similarly, under multiplication also it will satisfy. Now under multiplication again, you construct a table, then you will see that if you multiply this one, for example, 3 bar into 3 bar, it becomes 9. 9 on dividing by 6 gives you the remainder 3. So you have to write here 3 bar. Then say 2 bar into 4 bar, it will become 8. 8 on dividing by 6 gives you the remainder 2. So you have to write 2 bar. So you will see that all the entries here are the elements of that set 6 only. It can be 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. So this one, set 6, and addition modulo 6, multiplication modulo 6 satisfy the ring axiom. So therefore it is a ring. Now this is a ring with multiplicative identity 1 bar, because 1 here acts as the multiplicative identity, because for any A bar belong to set 6, 1 bar into B bar under multiplication modulo 6, this will be B bar only. You can see from this table that 1 bar into 0 bar is 0 bar, 1 into 1 bar is 1 bar, 1 into 2 bar it is 2 bar, 1 into 3 bar it is 3 bar, and so on. So it has multiplicative identity 1, and it is also commutative, because you can see again from the table 2 into 3 bar is 0 bar, which is same as 3 into 2. Similarly, 2 into 4 gives you 2 bar, which is same as 4 into 2, which is 2 bar, and so on. Therefore, it is a ring which is commutative and has multiplicative identity 1. But it is a ring with 0 divisor, because you can see that 2 bar belong to set 6. 3 bar also belong to set 6, where neither 2 bar is equal to 0 bar nor 3 bar is equal to 0 bar. But when you take the product, you can see from here 2 bar into 3 bar. What is the value? 2 bar into 3 bar, it gives you 0 bar. So therefore, here 2 bar into 3 bar is equal to 0 bar. So therefore, 2 and 3 bar are the 0 divisor of this set 6. Why? Because none of them is equal to 0, but the product becomes 0. So therefore, this is another example of a ring which has a zero divisor, or an example of a finite ring. Why it is a finite ring? Because it consists of only 6 elements: 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, which has a zero divisor. Now let me come to the next one, that is the properties in a ring. So if R under plus and dot is a ring, then we have to show that A into 0 is equal to 0, which is 0 into A. As we all know that this property holds for any number. For example, 2 into 0 is 0. But how to prove that in general that A into 0 is equal to 0, which is same as 0 into A for every A belongs to R. So let us prove that first property. Now we know that since R plus dot, this one is a ring. So we know that R under plus is an abelian group. So 0 plus 0 will always be equal to 0. Then multiply this one on both sides by A, but on the right. Okay, so A into, or I can write this one, 0 is equal to 0 plus 0. So multiply now A on this one. A into 0 is equal to A into 0 plus 0. So this implies that A into 0 is equal to A into 0 plus A into 0. Why this is possible? Because R is a ring, so it satisfies the distributive law, that is a left distributive law. So by left distributive law, A into 0 is same as A into 0 plus A into 0. But we know that 0 is the additive identity of R under addition. So you add this one, A into 0 plus 0. This will be A into 0 plus A into 0. Because A into 0 plus 0 is same as A into 0. So therefore, this 2 will be, to A into 0 plus 0 can be, A into 0 can be replaced by A into 0 plus 0. Now by left cancellation law, under addition, because R under plus is a group, so it will satisfy the left and the right cancellation law under addition. So therefore, A into this one, this and this can be cancelled, so you get 0 is equal to A into 0. So this proof that A into 0 is equal to 0. Similarly, you can show that 0 is equal to 0 into A, the same thing only. In the same way, you can show that 0 into A also will be 0. So now you see that given condition that R plus dot is a ring, then we'll always have this condition that A into 0 is equal to 0. Now let us prove the second property. Number 2, that is A into minus B is equal to minus A into B, which is equal to minus AB. So how to prove this property? Now we know that this one, A into minus B plus with AB. This can be written as what? Let us take this one. It is equal to A into minus B plus B. This is by again by left distributive law, as R plus dot is a ring. So A into minus B plus AB is equal to A into minus B plus B. But what is minus B plus B? It is 0, because R is a ring, R is a group under addition. So this is equal to A into 0, so which is A into 0. So this implies that A into minus B plus AB is equal to 0. Now if A into minus B plus AB is equal to 0, it means that the additive inverse of AB is equal to A into minus B. So this implies that A into minus B is the additive inverse of AB. But usually the additive inverse of AB is denoted by minus of AB. So it means that A into minus B is equal to minus of AB. Similarly, you can show that minus A into B also will be same as minus of AB. And let us come now to the next property, that is this one. Minus A into minus B is equal to minus A into minus B is equal to AB for every A and B. So now let us apply this one. We have to show that minus A into minus B is equal to AB. So how to prove this one? Minus A, start with minus A into minus B. By the second property, we know that A into minus B is equal to minus of AB. So now here it will be, take this one as A, then into minus B. So it will become minus of minus A into B. So this is equal to minus of minus A into B. And again this one minus a into b, by the second property again it will be minus into minus of ab. Now minus into minus become plus, so it will become ab. So we have that minus a into minus b is equal to ab. And number 4 property is that one a into b minus c is equal to what? This one we know that we have only the binary operation plus and dot, not minus. So how to write this one? You can write as a into b plus of minus c. And this is called a into b plus a into by left distributive law, because we cannot apply the left distributive law for this one directly because we have the operation only for plus and dot. So simplify this one, express it as b plus of minus c. So then only you can apply the left distributive law, as R and the plus and dot is a ring. So it will be a into minus c. But by the second property, what is a into minus c? It will be minus of ac. So this is called to ab, then plus minus of ac. So plus into minus will be minus, so it will be ab minus ac. So similarly, you can show that a minus b into c also will be ac minus bc by the same method. So I hope now it is clear that how these properties of these 5 properties in a ring holds. A into 0 is equal to 0, and a into minus b, how it is equal to minus ab, minus a into minus b is equal to ab, a into b minus c is equal to ab minus ac, and a minus b into c is equal to ac minus bc. So you go through again this explanation, and if it is not clear, you please tell me.